Good morning, good afternoon, good evening, ladies and gentlemen connecting with us from all over the world. My name is Kiara from the ITU, and it is with great pleasure that I welcome you all to episode 2 on IoT-based automotive emergency response system, which is part of ITU's webinar series on digital transformation for cities and communities. So I see a lot of participants connected today, and I look forward to your active participation during our discussion. I invite you all to drop a quick message down the chat box icon seen at the bottom of your screens, stating your name and the country from which you are connecting from. So we have an excellent panelist for today's discussion, and we are also very privileged to have in our midst Dr. Bilal Jamousi. So without further delay, I would like to give the floor to Dr. Bilal Jamousi, Chief of the Study Groups Department of the Standardization Bureau of the ITU, to give us his opening remarks.
Thank you very much, Kiara. Good day, ladies and gentlemen. Annyeonghaseyo to colleagues in Korea. I know it's late there right now. Konnichiwa, colleagues in Japan. It's my pleasure to welcome you to episode number 2 of the ITU webinar series on digital transformation for cities and communities. Today's webinar is dedicated to the theme IoT-based automotive emergency response systems, which is also known as eCall or emergency call in Europe. For years, ITU has been actively working to support the development of smart, sustainable cities and coordinate the deployment of information and communication technologies and digital technologies. It is not surprising that the automobile industry is one of the largest sectors for IoT use cases. Connected cars are using IoT devices to collect data, to inform drivers on road conditions, receive traffic alerts, and optimize route planning based on real-time conditions. For the purpose today's webinar, we want to focus on the fact that IoT systems are also offering drivers emergency assistance during road accidents. This is important for the simple reason that an effective automotive emergency response system can save lives. An IoT-based automotive emergency response system reports automobile accidents to an automotive emergency response center by an automotive emergency detection device. These three elements, the system, the response center, and the devices, need to be able to seamlessly communicate with one another to deliver rapid response in case of serious accidents, when every second counts. International standards and guidelines are vital in this regard. They contain technical guidance that ensure the interoperability requirements of these systems are met. ITUT Study Group 20 on Internet of Things and Smart Cities and Communities, which is the lead ITU standards group on IoT and smart cities, has developed standards that define the requirements and capability framework for IoT-based automotive emergency response system. eCall is an M2M service operating under codes +882 N plus 883, numbering ranges assigned directly by the ITU TSB director. ITU has assigned numbers under country code 882, 883 to global end-to-end providers for over 15 years. And we have identified an urgent need to bring greater clarity to the role played by plus 882 and plus 883 in systems such as emergency calls. ITUT Study Group 2, the lead on numbering, helps manage these codes and advises the TSB director on the allocation of these numbers. ITU technical standards are also helping to set the minimum data structure and data transfer protocol. Together, these standards can help implement automotive emergency response systems that can deliver swift emergency responses in times of need. I'm very excited today that we will learn more about the automotive emergency response system and how ITU standards are crucial for scaling up best practices and guiding its deployment. I would like to thank everyone for joining us today and wish you all a productive and informative webinar. Thank you.
Thank you, Dr. Jamusi. So before we delve into the heart of today's discussions, please take note of how the session will be run. All questions from the audience will be taken during the Q&A session after all presentations have been delivered. Participants can submit their questions by typing in the Q&A icon seen at the bottom of your screens. When submitting a question through the Q&A icon, kindly type first the name of the panelist to whom the question is addressed, followed by the question. If the question is addressed to the panel in general, please type your question directly without the name of the panelist at the start of the message. Kindly note, the workshop is being recorded and the recording will be made available on the event website. All the presentation materials will also be made available on the website after the event. Please be informed that closed captioning is available for this event. You may turn it on by enabling the closed captioning icon on your screen to get a text stream of the speech of the speakers. Before we officially start, we would like to specially thank Mr. Junsub Lee, Question 1 Rapporteur of the ITUT Study Group 20, for all his efforts to make this webinar possible. So now, I would now like to call on Dr. Hyung-Jun Kim, Working Party 1 Co-Chairman of ITUT Study Group 20, and also the Senior Vice President for Intelligent Convergence Research Lab of ETRI, to lead us through the session. Dr. Kim, the floor is yours.
Okay, hello, Chora. Thank you. My name is Hyung-Jun Kim. I'm very happy to moderate this today's ITU webinar session, which is mainly focused on IoT-based automotive emergency response system. So as Bilal Jamoshi, he already expressed at his opening remark, the automotive emergency response system is very important. We call this kind of a system as emergency call in European Union. So at today's ITU webinar session, we'll have the four distinguished speakers who are mainly focused on this subject. So I'm very happy to moderate this session. Thank you. So first of all, I would like to recall the time when we are having very the technical discussion at ITUT Study Group 20. A couple of years ago, cause of this the technical situation, I mean for this emergency call system or emergency call devices, we need to make as a standards there in ITUT Study Group 20. So I have something experience to develop with the relevant ITUT recommendation there in ITUT Study Group 20. I will also welcome the relevant speaker at this ITU webinar session today, especially they are mainly related to the development of this ITUT recommendation. So first of all, I would like to introduce the first speaker for this the ITU webinar session. Dr. Taeyong Shim, he is work for ETRI, where he is currently the senior researcher, and he had the deep experience to develop the international standards there in ITUT Study Group 20, including ITUT YDAT 4119 and 4468, as well as the several domestic standards for automotive emergency response system. So please welcome him for his presentation. And during this 2-hour session, each speaker will deliver up to 20 minutes the presentation. So Dr. Shim, the floor is yours.
Can I share my screen?
Sure, please.
Okay. Okay. Good morning, good afternoon, good evening. Thanks for attending this talk. I'm Taeyong Shim, senior researcher from ETRI Korea. It's my pleasure to present this presentation. Thank you, TSB and moderator Hyungjun Kim for inviting me. Thank you. This talk is designed to inform you the ITUT standard status of the AERS automotive emergency response system. From this presentation, you will be able to understand the international standard for the AERS. I will be dealing this topic with reviewing ITUT AERS standards. There are 3 main things dealing in my presentation. First, YDAT 4119 for requirement and framework for the AERS. Second, YDAT 4467 for external related data structure. And lastly, YDAT 4468 for data transfer protocol for the AERS. Before starting to dive into the AERS, I will introduce our research institute, ETRI. Over 45 years, ETRI has contributed to the nation's research, development, and distribution of industrial core technology. In this field of information, communication, electronics, broadcasting, and convergence technologies. And now, ETRI leads the first industrial revolution in AI, big data, cloud, and IoT. Please visit our website. Thank you. Shortly, let me start by saying just a few words about myself. I have developed ITUT YDAT 4119 with co-editor with Junseop Lee. This standard is started to development as a new work item in March 2017 and approved recommendation in March 2018. Also, I have developed the ITUT YDAT 4468 with co-editor with Junseop Lee. YDAT 4467 and YDAT 4468 were started to develop a new work item in January 2018 and approved in January 2020. So, without further ado, let me move on to the main part. I'm going to share ITUT YDAT 4119, the requirement and capability framework of the AERS. Every year, more than 1 million people die from car accidents. To reduce the fatalities, automobile industry spend a lot of money and effort to improve vehicle safety every year. However, when fatal accidents are unavoidable, efficient response rescue procedures are necessary, such that victims can be transferred to the hospital within the golden time. As you can see here, employing ARS is expected to reduce the accident detection time T1 and report time T2 by using automatic accident detection report procedure. In addition, the arrival time at the scene T4 will be significantly shortened by utilizing geographical position information provided by the ARS. The purpose of this standard is to identify requirements of the ARS for aftermarket devices. The ARS is designed to bring rapid assistance to driver and passengers in an accident. The ARS include ADD and ARC. ADD means automotive emergency detection device. AERC, automotive emergency response center. In the event of serious road accident, the ADD in the vehicle automatically connect to the ARC and give the accident related information. It includes GNS coordinate, the time of the accident, and VIN number, etc. This slide represents the capability framework of the ARS. SOS button enable manual EA request. Vehicle state monitoring FE obtain information from vehicle sensors to aid ADD. OBD2 scanner is an example of the implementation. Location FE obtains geographical location information of the vehicle using satellite or cellular networks. MSD generating FE generate on MSD if an ADD detects accident or SOS button is pressed. Voice call FE receive a voice call from proxy or ARC FE. Proxy ARC FE receive an MSD from ADD, confirm, including filtering out false alarms and forward the MSD to ARC FE. If EA dispatch is necessary, transfer the call to ARC FE. ARC FE finalize the analysis of the accident and request EA dispatch if necessary. In this slide, this procedure represents the workflow in case of EA dispatch request. Step 1 to 4. In case of accident detection, one manual EA dispatch request on ADD generate on MSD and transmit to the proxy ARC FE. And step 5. The ADD notify user accident detection event and ask for confirmation. Step 6 and 7, the ADD or the proxy ARC automatically confirms accident if a user fails to confirm within the timeout period. Step 8 and 9, using the information in the MSD, the proxy ARC automatically initiate callback. If the call is not answered within timeout period, it confirms the accident. Step 10 and 11, based on the accident confirmation, the proxy ARC forwards the MSD to the ARC FE and transfer the call to the ARC FE. Step 12, the ARC obtain additional information from the users via voice call to confirm the accident. Step 13, if the accident is confirmed, the ARC requests EA dispatch based on the MSD. Step 14 and 15, the call is terminated when EA dispatch arrival on the site. ADD implementation example have 3 categories. In this slide, this figure indicates in the case of the ADD without data and voice communication capability. This example could be navigation system, or dashcam, etc., using data communication and voice communication of users' phone. Let me move on to the next standard. We can see IoT WIDA 4467, minimum set of data, MSD structure. This recommendation is to specify the external related data, so-called the MSD structure. An MSD is composed of mandatory and optional information. The mandatory information shall be included in the MSD when an MSD performs normal operation. The optional information can be additionally included to give more information to the AURC. As shown in this figure, an MSD needs to be sent from ADD to the AURC. If you look at this figure indicates the MSD structure. An MSD is composed of MSD version, mandatory information, and optional information. MSD version means the version value of the MSD. Here is a slide of mandatory information listed in this table. This table is a set of information when the ADD performs normal operations. Message identifier, timestamp, control type, vehicle type, and VIN number, vehicle direction, and codec number, etc. All of this information is mandatory information in MSD. I will show you some of representative mandatory information. Firstly, at this slide, control type in control information indicate a set of automatic activation, test call, position trusted, and cancel request. Automatic activation is true means an MSD is automatically created, or first means that is manually via the SOS button. Test call is set to true means an MS send is for service testing purpose. Position trusted is true means GNSS is used to obtain location information. Cancel request is true means the MSD is used to cancel previously sent message. So secondly, vehicle location indicates the location information at the time of the extant detection. The vehicle location value consists of latitude and longitude values. MSD encoding law adaptive CBOR defined in IETF RFC 7049. In this example, the result of encoding MS message has 106 bytes totally. Optional information is additional data not defined in mandatory information, but correlated with the extent. For example, information to determine the severity of an extent, G-force value, vehicle velocity, etc. The optional information is expressed as a pair of object identifier or ID and the additional data. Let me move on to the last standard ITU-T Y.4468 MST transfer protocol. Y.4468 specifies an MST transfer protocol between ADD and ARC. This standard defines protocol parameter and message type and operation sequence of MST transfer protocol. MST transfer protocol operates over the CoAP IETF RFC 7252. CoAP provides a request response interaction between ADD and ARC in order to report to a cancel automobile accident. In this slide, this figure indicates the sequence of request response operation between ADD and ARC. Step 1, 2, 3. In case of accident detection, ADD generate an MST and transmit an MST notification message to the ARC. Step 4, the ARC decide to pitch back the response when it does not need longer time to obtain the response code than ECK timeout. Then go to the step 5. Otherwise, the ARC chooses the separate responses procedure, then go to the step 6 to 9. In step 5, the ARC sends back an ECK response message with the response code. At 6 to 9, once ARC immediately sends back an empty ECK message. When the ARC finally has issued the response code, it transmits a conformable response message, and then the ADD sends back an empty ECK message to the ARC. Step 10 and 11. In case of a cancellation request is triggered, the ADD transmits an MST cancellation message to the ARC. Otherwise, ADD terminates this operation. MST message have two kinds of request type messages. One is MST notification message, and the other is MST cancellation message. MST notification message is for reporting on accident. CON is type for transmission reliability. Post code for create information or notification. Message ID for detect message duplication. Token used to match with the response messages. MST cancellation message is to cancel reporting the accident. This message indicates the cancel request of control type in the MST changed to true, like this. MST message have three cases of response messages: ECK response message, empty ECK message, and conformable response message. ECK response message is for notifying the successful reception of the message. Empty ECK message is for an empty message code without input. Conformable response message is for indicating success or failure of MS processing result. You can see which message is used in the ARS of the sequence of the MST transfer protocol. To wrap up my presentation, I would like to emphasize that the ARS is the unique emergency system for the vehicle currently on the road. with the ARS, the victims can be transported to the hospital within the golden time. It will dramatically decrease people die from car accidents. That's all I have to say for now. Thank you very much for attending. Thank you.
Okay, thank you so much, Dr. Shim, for your kind presentation. At the very beginning of today's session, as I already, the session moderator, she already explained you, we will have four presentation first. So after all the presentation, we will have the small Q&A session until the time is allowed. So please, if you have any kind of question to each speaker, please put your question to the note, or anyway, please give me or the organizer of this session for your question. Then we will get all your question to deliver your question to each speaker. So thank you again, Dr. Shim, for your kind presentation. And with that, I would like to invite the second speaker, Mr. Daewon Kim. He is now work for the bigger the company department in the Thinkware Corporation, which is the rank #1 market share of aftermarket navigation system and dash cam. So he is also one of quite technical technician. So I would like to invite him for his kind presentation. So Daewon Kim, would you please give your presentation? You will have up to 20 minutes. Thank you.
Okay. Okay, I will share my presentation. Just a moment, please. Okay. Can you see my presentation?
Yes, we can see your presentation.
Right.
Please go ahead.
Okay. Thank you. Hello, everyone. I'm pleased to meet all of you here today. My name is Daewon Kim, and I'm a director of Vehicle Component Department at Thinkware in Korea. Today, I would like to present ECO and ADAS combined device, its benefit and potential business opportunities. Let's get started with Thinkware company overview. Thinkware began with location-based service car navigation system in 1987 in South Korea. It has expanded to dashcam and automotive components area. As progress, it occupies one of the top brands and significant market share with strong intellectual property and patents. Thinkware owns, just a moment, please. Thinkware owns a factory that is capable of 2 million units per year in South Korea. We are collaborating with another factory in China for BMW. Also, Thinkware has many automotive OEM, ODM, DIO references. Since 2020, Thinkware has been a tier 1 supplier of Hyundai Kia Motor Company and BMW. For the Korean market, Thinkware covers all aspects of value chain and provides excellent customer satisfaction. Thinkware delivers one of the best value to the customer for the global market with its branches and sales channels. You can see US, Canada, China, and Japan branches. and many sales partners around the globe. Here are some evidence for the global brand competitiveness, such as recommendation from famous IT media, twice winner of CES Innovation Awards, and many international product design awards as well. Now I would like to show you dashcam technology. Most of these technologies are driven first by thinkware in the market. Particularly in connected dashcam service, thinkware has provided a kind of a proprietary eco-service for more than 5 years. But it turns out there are limitations in proprietary eco-service. Initially, the cost should be higher on both operation and the device price. High cost leads to a low market penetration rate. The small number of customers leads to high operating costs again, and reduces the chance for direct collaborating with a rescue agency. As a result, it ends up with delayed rescue and no customer satisfaction. So we need to step to the next level. Here is thinkware first eco and ADAS combined device. This device consists of 3 parts: camera, main controller, and touchscreen indicator. Main features are composed of 3 functions: ADAS, eco, and dashcam. It has deep learning capable CPU and GPU with automotive 9-axis IMU sensor and ultra-sensitive image sensor that can detect lanes and vehicles at night, even without headlights. Let me show you a short demo here. Okay. Left side of the recorded screen, recorded in this device. So you can see everything, including lanes, vehicles, and etc. While the right side, you can see nothing but taillights. Sometimes in extreme weather condition, human eye can't see lane mark like this. At the bottom of the left side, you can see estimated distance in the meter unit, 107. All right, next. Here's a Korean NCAP for the collision warning test result. And lane departure warning test result. With this kind of NCAP style ADAS test results, I can say that ADAS quality is the same as automotive products. You can see a wide range of environmental and electrical specification test results that gives product reliability, especially in hardware. On the other hand, precise accident detection and analysis are essential for eco. thinkware has been collecting more than 4,000 real-car accident video with IMU data by now. 2,200 actual car accident data and several crash test data has been analyzed. I will show you two examples here. First, this is a collected real car accident video. And second, eco crash test video. You can see raw data on the left side, after calibration data, and impact amount estimation, respectively. So with this algorithm, we can analyze type of accident, what is really happened. This device isn't just prototype. Think we sold about 20,000 units in the year 2019 in Korea with the help of government ADAS subsidy program. But unfortunately, there was no available automatic emergency response center. And I had to make the eco feature disabled and remove some hardware parts. Back then, there was no choice, but you can see, as you can see, significant effect. Injured people had reduced 34%, and accident had decreased 30%. What an impressive result. But when it comes to fatality, the decrease was only 16%. Why? Well, this result comes from ADAS, not from eco. As far as I can see, none of the ADAS today can prevent fatal accident perfectly. However, I believe if we could have eco, we would see more fatal drops in tomorrow. So why should we consider ITU eco in the first place? First, it's based on the international standard, not proprietary. So many companies can participate, encouraging competition and reducing cost. Second, we can apply it to new car and large number of existing cars effectively. As a result, ITU eco will be more affordable and cost-effective way to save life, and we'll be able to reduce tremendous amount of social cost from the car accidents. Okay, here is the installed accident, installed year. Right. Last page. Thinker is looking forward to wide adoption of ITU eco in the glove. Then you'll see many life-saving and more sustainability. I hope to see that moment with you soon. We want to find business opportunity with you in many ways. For example, we can provide a turnkey solution, perform POC project with you, sell our reference hardware and software, or we can make it even better. Please don't hesitate to get in touch with me if you need more information. Thank you. I appreciate your time and attention.
Okay, thank you so much, Daewon Kim, for your kind presentation. I believe the participants to this ITU webinar session, they have kind of questions. So please put your question in Q&A chat box. So after presentation, I would like to deliver each relevant question to the relevant speaker. Okay, so with that, I would like to move on to the third speaker at this technical session. The third speaker, his name is Dr. Junuk Lee. Actually, he worked for ATRI till the year 2013, and after that, he moved to the software company called Handysoft Corporation, and now he is working for AIB rep from the year 2019. So I would welcome him for his presentation. He will mainly focus on the implementation of automotive, the Emergency Response Center. We call this as AERC. So Dr. Lee, please, you have the floor.
Thank you, Dr. Hyungjun. This is Junuk Lee. Can you see my presentation?
Yes, I can hear you. I can see your presentation. Please go ahead.
Okay. Hi. This is Junuk Lee. I'm a research fellow at IBRAP in South Korea. Today, I'd like to present the AERC implementation, which is Automotive Emergency Response Center, according to the IoT standard, and some business cases in South Korea. The table of contents is as follows. First of all, I'd like to introduce our IBLab, and then I'll show the AERC implementation cases, and then business application cases in order. IBLab is an AI platform-based solution and service vendor in South Korea. We are supplying standard-based IoT and AI platforms to the Korean market. In addition, based on this platform, we are developing and supplying smart work, smart factory, smart city, and connected car solution to various companies in South Korea. In 2019, we spawned off from Handysoft as an AI specialized company. Handysoft is a representative software company in South Korea with long experience and history in South Korea. In the days of Handysoft, we accumulated many excellent business cases with various partners through the supply of domestic IoT solution. These partners include companies in home appliance, apparel, sport, medical device, and so on. Based on this experience, we have started as IBRAP, and we are continuing to provide AI-based service through big data analysis. Our IBLab, the strength is that we have IoT and AI platform technology, which enables us to provide service in various fields, from company, factories, home, and cities to bakers. iWorks is a solution for smart work. The goal is to collect various IoT data in work environment, turn into big data, and ultimately provide more efficient collaboration and convenience workspace through AI learning with domain knowledge. In the COVID-19 era, non-face-to-face and flexible work is important. More flexible work management and access control automation are required in many companies. And work environment control and collaboration support have became important. IBRAB is realizing various services that converge IoT and AI in South Korea, and we are preparing for overseas marketing. Our next part is about ARC implementation cases. ITD standard, the Y.4119, defines the capability frameworks of AERS, as shown in the diagram. In the event of an accident, AEDD, which is automotive emergency detection device, generate MSD data and transmit it to AERC so that AERC automatically and efficiently handle the emergency request. In accordance with the standard, the AERC responds to the emergency request and determine whether there is an accident. And if the dispatch is necessary, notify the EA, the emergency authorities, which is emergency authorities. As with the standard framework, the implementation system in South Korea also include AEDD, AERC, including EAs, such as fire department, insurance company, vehicle monitoring company, and towing service company. Based on the standard, our solution has completed tests interacting with various AEDD terminals, along with Korea's TTA, the standard agency. For communication with the terminal, co-app defined in the MSD standard protocol is supported. And also, it is possible to link with external control system according to the proxy PSAP applications. Regarding to the workflow of AERC, figure 4 shows the overall flow of the dispatching an emergency request to the EA. And figure 5 shows the workflow when the user cancels the emergency call via AEDD. Our proxy PSAP support instant incident location tracking. In the event of an accident, the location is automatically tracked and accident information can be monitored easily. In addition, proxy PSAP queries and provide incident information so that you can inquire what information each instance is and how it is currently being processed. This figure shows more detailed accident information. According to the Y.4467, MS data in COAP format can be checked in detail. In addition, our implementation, each accident data is stored and managed. And if necessary, it can be exported in Excel format. And the accident information reset or email notification to the administrator is also supported. From now on, I'm going to show a short video about our AERC implementation.
Hi, hello, Dr. Junok Lee. May I
Yes.
interrupt you? I'm not quite sure whether or not I lost your voice or sound.
Yes. There are some problem in the video showing. So it is not easy to show the overall videos. So I need to skip this video. Okay.
Okay, thank you. Yes, I believe it's more it's better than to keep the current situation. Thank you.
Thank you. Although it is not stage of the commercializing this ARC standard technology in South Korea, there are some business related cases, this standard technology, which I'd like to introduce. IBRAP has conducting business based on the connected car platform in cooperation with partners since the days of Handysoft. One example is application of rental car service. And the other is the application of solution development with vehicle insurance company. The connected car platform can collect and analyze driver and driving information from multiple devices, including OBD2 devices, mobile phone, and also provide useful function for various service using the API. Through this, rental car and fleet management service and insurance company linking service and etc. can be provided based on the connected car platform. AERC function is not integrated in our existing connected car platform, but the implemented AERC will be applied to the service to provide more advanced service in the future. Our existing connected car platform focus on collecting and analyzing driving information and providing services by analyzing vehicle control and safe driving habit. Now, by applying AERC in connection with accident data from these vehicles, each business partners can have a feature that can support more efficient emergency response. Jeju Island is a representative tourist island in South Korea. Various rental car markets are formed. In 2019, we signed an MOU with Jeju Pass company and conducted several demonstration projects. In this demonstration, driving information was collected using an OBD2 device with built-in communication and GPS functions. Two types of user service are provided, and mobile app provide driving information and driving score service related to safe driving habit. And the web application provide vehicle location tracking and trip history and trip event and driving scores. We provide a variety of useful services such as location and diagnosis, safe driving, and reporting. Through this pilot demonstration, this device was installed in a rental car, and data collection and monitoring functions was verified through operation in various regions of Jeju Island, and we were able to confirm the usefulness and strengths, and that this function will be have when integrated in the rental car services. Our next step is to go one step further from this rental car demonstration and provide services by integrating the AERC functions in relation to the emergency rescue. Through this, we will be able to provide a differentiated and superior service from other various rental car service companies in Jeju Island. In South Korea, vehicle insurance company are also thinking a lot about the pricing policies or providing additional service based on the driver's driving information. As you know, PAYD, paid, is the concept of paying a fee based on the driving. But until now, the most Korean insurance company are using discount policy based on the driving distance. Safe driving habit lower the accident rate, and the benefit are important to the insurance company. We are currently working with the major domestic insurance company to collect the driving information and analyze and apply it to the insurance service. It can be seen as another application cases based on the connected car platform, like Jeju cases. In this project, only mobile phone with have multiple sensors are applied to collect the driving information, and analyze and monitoring function are provided. Location, driving log, driving distance, and the dangerous driving factors are using various sensors of smartphone can be collected. The insured customers will be offered the following applications: driving score service, driving information service, and driving information service. After developing this solution, we are preparing for the next step. It is to provide emergency rescue systems such as AEDD and AERC to the B2B market. The reason for paying attention to this service is that it can be the first case in South Korea that provide differentiated insurance service based on the AERC function that follows the IoT standard. Here is what I've prepared today. Thank you very much.
Okay, thank you so much, Dr. Lee, for this kind presentation. So with that, I would like to invite the last speaker for today's session. His name is Jamin Zhang, who is work for TTA, the Telecommunications Technology Association. It's a kind of domestic, the standard association in Korea. And he will mainly focus on the conformance test system for IoT-based automotive emergency detection devices. So Jamin, you have the floor. Thank you.
Could you see my presentation and listening my speak? Hello?
Yes, I can hear your voice. Please go ahead.
Thank you for introducing him, Kim, and thank you for inviting and giving a chance to present at here ITU. Good afternoon, everyone. I'm Jamin Jang, Senior Researcher at TTA in Korea. What I'm going to talk about today is conformance test system for IoT-based AEDD. The presentation will focus on how the conformance test system is configured and how we verify the implemented test system. Let's see. Since the presenters explained about eCore in the previous presentation, I think you have understood how eCore works. In this chapter, I will explain the development of conformance test system for IoT-based AEDD. A brief description of the process in which the eCore operates can be divided into 4 steps. The first step is to detect an accident from AEDD, and the second step is to transmit MST to PTAP. Then the third step is to analyze and notify an accident to emergency authorities, and the last step is to respond. The conformance test system we developed cover the part in the square marked with a red dotted line in this figure. In detail, on this part is required to verify whether the function required for the AEDD is normally implemented. Therefore, PSAP should be able to communicate with the AEDD and analyze the received MSD. eCore components test system can be largely divided into logical and hardware configuration. Left figure shows logical configuration, and the right figure shows hardware configuration. Logical configuration consists of eCore signal analyzer, base station, and GNSS signal generator. As shown in this figure, eCore signal analyzer can control all the components that make up eCore component test system. And if the AEDD is approached, it can also control the AEDD. To briefly explain the operation process, AEDD can receive the GNSS signal such as GPS or Galileo on GLONASS. The signal GNSS signal generator transmits. And then when AEDD detects an accident event by automatic or manual mode, it generates MSD and encodes in CBOR. The generated MSD is transmitted to the eCore signal analyzer through the base station using LTE and the CoAP application protocol. In eCore signal analyzer, the received MSD is decoded and analyzed for displaying information to the tester, and the tester checks whether the AEDD has operated normally. The tester determines whether to connect a voice call to callback number included in the MSD transmitted by the AEDD. In hardware configuration, GNSS signal generator and the base station were composed of SMBV100A and CMW500 of RNS, which are widely used in the mobile communication tests respectively. So the conformance test system was developed jointly with RNS. We developed by implementing each protocol used in eCore on commercial equipment such as SMBV100A and CMW500 as seen on the previous page. Each protocol has developed in compliance with each international or domestic standards. Red Record are all international standards. Basically, CBOR and CoAP were developed in accordance with IETF international standards. CBOR is similar to a method of expressing data such as JSON or XML, but has the advantage of having a small data size in a binary object type encoding method. QAM is primarily a protocol designed to transmit data from low-power IoT devices to servers and utilize the UDP protocol-based request response model. In addition, confirmation messages and timer management options are provided to enable reliable communication. Both CBOR and the CoA protocols used in equal take into account the purpose of the equal system, which focuses on data weight reduction and efficiency to process and transmit information as quickly and reliably as possible in case of vehicle accident. But there are some differences between IETF standards and domestic standards in using QA protocol. It means that some fields are not used in QA packet header, such as optional fields. And some parameters default value for transmission are not same. For example, domestic standards require shorter time to respond to AEDD than international standards. International standards define response time at 1.5 seconds. This is the time that PSAP takes to analyze after receiving MC and should selectively respond the method with the AEDD depending on the expected time it takes. Given that such parameter value are protocol for emergence, they are sufficiently acceptable. As a result, we completed the protocol hierarchy in compliance with both international and domestic standards and verified that it operates normally. As a result of the previous development, we were able to make 11 test cases. For development, the entire equal service process was divided into detailed stages according to main courses at first, and the parts that should be checked as essential for each step of transition process were derived as test items in consideration of the characteristic of the AEDD. Since there is a correlation between each derived test item, and it can include a repetitive process, it is necessary to develop a test case for efficient test performance. The test case can be classified into several steps according to the operating state of the AEDD. In each step, in order to verify the function of the step, the environment and step-by-step transition test criteria for interworking between the AEDD and the conformance test system were defined. The defined environment and transition test criteria were composed of test cases for AEDD could be executed by equal signal analyzer. So all 11 test cases are for the conformance test of AEDD, and each test case has a similarity, but the results to be confirmed through the test are clearly different. To explain a few of these unique cases, TC5 was hard to develop. The power supply should cut off the main power to AEDD at an appropriate time while the AEDD processes the accident event. The AEDD must maintain the accident handling processing operating normally through auxiliary power. It is important point that AEDD should cut off the main power from the power supply by catching the moment of the operation process of handling the accident event. Not all test cases are mandatory tests for AEDD. For example, in the case of the ADD supporting only Wi-Fi or Bluetooth, TC11, this protocol connection, may not be supporting. Specific test results for ADD, some ADD samples will be described in the later chapter. Now, this chapter shows several samples that have verified the implemented test system. 3 cases have been prepared, ADD that support LTE, Wi-Fi, and Bluetooth, respectively. All tests are conducted within a shielded space disconnected from external communication. So ADD can only communicate with the GNSS signal generator and base station. The first case is a test result for ADD supports LTE and voice calls. At the time of the completion of the development of the conformance test system in ADD, which supports both LTE and voice calls, has only smartphone app type. This type of ADD was developed by Atri, and we were able to check with each other whether its developed was properly implemented according to each standard. As a result, this ADD successfully supported all except 55 test cases shown in the previous slide. Smartphone cannot use additional power supply because main power is supplied through their own built-in batteries. Therefore, it is impossible to apply a mechanism capable of blocking power supply while the ADD processes an accident event. The second case is an ADD that supports only Wi-Fi. In this case, a device that supports Wi-Fi tethering, such as a smartphone, and can use LTE should be prepared before this test. The ADD we tested was a navigation type that collects information necessary for accident detection through its own sensor and determine accident occurrence according to algorithm. However, since ADD does not support voice calls, the callback number in MSD must be entered directly by the tester and only check if the matches the value entered through the signal analyzer. Unlike the previous test case 1, this ADD is supplied to main power through external power supply. In addition, auxiliary power was installed inside this ADD, so TC5 could be successfully tested. As a result of this test case, the ADD successfully tested all other TC except TC11, that is voice call connection. The last case is an ADD that supports only Bluetooth. In this test cases, a Bluetooth pairing device may also be considered an ADD. In other words, the two devices are grouped together to become ADD. The characteristic of ADD supporting Bluetooth is that it collects only sensor information necessary for accident detection, and then transmits all of the collected information to a Bluetooth connected device. Then the device could detect an accident using received information and generate an MSD and transmit it to the equal signal analyzer. An example of this case is, as you know, VSM vehicle status monitoring, such as OBD2 scanner. However, in this case, it was tested with PC installed a program that can perform operations similar to OBD2 scanner. The purpose of this test case was to check that the AEDD supporting Bluetooth was also testable, and there's nothing special about this test case. That's all I have prepared for you today. Thank you for watching my presentation. If you have any additional questions after the presentation, don't hesitate to send me an email. Thank you.
Okay, thank you so much, Jamin, for your presentation. So we have complete all the presentation. And so far, I think we still have about 30 minutes for Q&A. So while we are having each speaker's presentation, I have checked the Q&A box, and I saw a number of the feedback from each speaker regarding the question by the participant. However, if you have any further question or any comment for the clarification, please put your message to this Q&A box. Then the relevant speaker will reply back to you with his feedback. Okay. So any question? So now we are going to have a Q&A session. We have complete all the presentation by each speaker. So I have checked the Q&A box. So in the meantime, I would like to ask a question to each speaker. So first one, I would like to give the simple question to the first speaker, Dr. Sim. During your presentation, you mentioned about the proxy AERC. So could you explain more the capability of this proxy AERC? Why this function is needed? Thank you.
Can you hear me?
Sure.
Yeah. The proxy AERC received on MSD from the ADD confirmed, including filtering out false alarms, whether an accident occurs or not, by using the automated system, and forward the MS to the AERC and transfer to the call to AERC if EA dispatch is necessary. Considering the features of aftermarket devices, I'm sure that the AERC needs to be equipped with false alarm filtering functions. So, well, proxy AERC is needed. Thank you.
Okay, thank you, Dr. Sim, for your the prompts feedback. And my second question is directly go to the second speaker, Daewon Kim. In your presentation, you explain the combined device between eCall and ADAS. So what make you decide to combine eCall and ADAS in one device? Is there any advantage? Thank you.
Actually, I think we implemented 3 things: ADAS, eCall, and dashcam into one device. There are some reasons. First, preventing is always better than rescuing faster. Second, the installation cost is relatively high, even with one featured device. In other words, we can make one featured simple device cheaper, but then the installation cost is almost the same level as the device itself. Last but not least, driver wants to have dashcam function if it has a camera in any way. This is the reason.
Okay. Okay, thank you so much for your feedback, that one. With this, I would like to ask you the second question, that one. What are the advantages of IoT equal when it is compared to with others? Because as you mentioned, your work for the thinkware is the domestic the market share rank #1 in Korea. So you are work for the manufacturer. So in this regards, may I kindly ask you what are the advantages of IoT equal when it is compared to with
Yes.
others? Thank you.
That's a great question. With the proprietary eco, I already remarked its limitations in the presentation. IT eco is cost-effective and easy to adopt than other standard eco such as EN 15722 or IETF RFC 8147. Without an expensive automotive mobile communication module, it can work with driver's smartphone tethering. So we can install it in a new car and existing cars. The penetration rate is essential when you want to see impressive result. Let me give you one example. In 2090, the Korean government subsidy program applied only 20 tons of heavy-duty trucks. That is less than 10% of all trucks. You can see only 6 to 10% of drops in the year 2020 data. Not impressive at all. Why? My assumption is just simple. Car accident happens with other cars. Usually not happened alone. Let's imagine 2 cars involved accident model. We randomly pick up 2 toy cars out of the box, and containing only 10% of toy cars have equal. Then we will get about a 20% chance to get at least one of them have an equal. But if 50% of toy car in the box have equal, we will get about 76% chance of being rescued with help of equal. So we better spread equal widely.
Okay, thank you so much, Devon, for your the response. And Junok Lee, Dr. Lee, I also would like to give you the simple question. While listening your presentation, what are the strengths of the use of AERC in Korean automobile related business?
For the question, in Korea, in South Korea, the vehicle-related service sector, the BM service providers such as Hyundai or Kia Motors now provide emergency service such as the SOS call. But we think, however, there is no cases in South Korea that apply the standard-based technology such as ARC for emergency rescue in various B2B market. I believe that if it entered the Korea's AM market quickly based on the standard, it will have many advantages in competitiveness. That's all. Thank you.
Okay, thank you, Dr. Lee. Additionally, may I ask the second question to you? What efforts are you currently making to apply this AERC?
Good question. I presented 2 kinds of business application example in this presentation. but the previous two business application examples are still under discussion. In fact, Jeju rental car market is saturated, and new attempts are needed in terms of competitiveness and service. It is difficult to make faster progress due to the Corona period, but we are concentrating on this path. In addition, in the vehicle insurance company ranking service, which will be held until the end of this year, we are preparing to think that this emergency rescue link will be very meaningful proposal for system improvement in the next year. So we are preparing two kinds of attempt to increase our competitiveness. Thank you.
Okay, thank you so much, Dr. Lee, for your answer. Okay, now I would like to go down to the very last speaker to this question, to this session. So, Jamin, simply to question, is the developed test system currently on the market? And my second question is, have you tested the commercial AEDD with test system? Thank you.
The first question is in Korea, there are still several problems that have not been resolved, such as legal issues, communication, or test specification regarding equal. Therefore, there's no demand for component testing ADD, so the test system has not yet been released. Second answer of question, domestic standards have already been published, and some vehicle manufacturers or device manufacturers developed them according to standards, and they have asked us to test them. However, it is not commercial because ADD was developed for just testing. And I'm sorry that I can't mention the specific manufacturer's name. So thank you.
Okay, thank you, Jamin, for your answer. Still, we have a time for Q&A. I have the double check with the Q&A box, but so far no more question at this moment. So may I ask one more question to Dr. Shim, the first, the presenter. So
Yes,
in your presentation, the AERS is required for providing bidirectional voice call capability. Could you explain how a callback is initiated?
Thank you for your question. In case of an EA dispatch request, the AERS try to bidirectional voice call back to the user driver with his/her callback number over VoIP or any voice call. During callback, the AERS obtain additional information from the user to confirm the action. Thank you.
Okay, thank you so much, Dr. Shim. And I'm checking always the Q&A box. I believe we have received a number of questions, but mostly I believe it was reserved. But so far I have a question from Marco Carucci, the one of my close friend. He put his question to Daewon. So Daewon, Kim, could you double check with Q&A box? And
all right.
If necessary, please give your feedback. Thank you.
All right.
Any other question or comment? I'm checking the chat box. Okay, no issue. And checking the Q&A box. Yes, I believe that one he is now replying back to Marco Carucci. And with that, I see no further question from the remote participants. May I ask once again, are there any question or comment for clarification to speakers for today's IT webinar session? I see no one asking the floor. So still we have time, but if there are no further question or comment for the clarification, I would like to the end and the today's IT webinar session. So for closing remark, we have Mr. Toru Yamada, the co-chair of, co-vice chair of IoT Study Group 20. So Toru, would you give your final the remark for the conclusion? Thank you so much.
Hi, thank you very much. Thank you, Hyunjun, for the excellent moderation. Also, thank you very much to our speakers for joining us today and sharing their valuable insights. And thank you very much to all participants for taking the time to join us today. Well, good evening from Tokyo, Japan. Okay. Also, I have to say good morning and good afternoon to everyone. I'm Toru Yamada with NEC Corporation, also a vice chair of the IoT Study Group 20. So today, we have discussed the importance of the interoperability and the seamless connection in the IoT-based automotive emergency response system. As the speaker mentioned, the ITU has already developed some standards for automotive emergency response system. They provide the guidance for setting the minimum data structure and the data transfer protocol. And now, still, ITU is actively working to develop more international standards that will enable us to coordinate the deployment of the response system, response center, and the other connected devices. So we welcome your participation in development of such standards in ITUT Study Group 20. At ITU, we strongly believe that the digital transformation or the transition to smart city should focus on people, not on the technologies. That's why we want to put a word, sustainable, in smart city. I mean the smart, sustainable cities. And we work to ensure that no one is being left behind. To do that, we believe meaningful and global level collaboration and partnership are key factors. So I want to encourage you to join us in the rest of ITU webinar series on digital transformation for cities and communities, and share your views and opinions with us. Next webinar will be held in September 16, the day after tomorrow. The topic will be smart, sustainable city architectures. It is also a very important topic for the digital transformation for cities. I hope your participation. Okay, once again, I want to thank everyone for taking the time to join us here today. I hope that you found that webinar to be very useful. If you have any questions or feedback regarding the webinar or the work of ITU on smart sustainable cities, please feel free to reach out to us. And please also be informed that the highlights of this webinar, including key recommendations, along with all presentation materials, will be available on the IT website. And you can also find our contact information there. I hope to see you again in the next webinar session. Thank you very much for joining us today. Thank you and arigato. Goodbye.
Thank you, Mr.
Okay,
Yamada. And thank you, Dr. Kim. Thank you to our panelists for that insightful discussion, and to Dr. Kim for the excellent moderation. And of course, to all the participants for attending today's episode. So we would like to take the opportunity to invite you all to the next episode, as mentioned by Mr. Yamada, episode 3 on smart sustainable city city architectures, challenges and opportunities. We have also shared the link to the list of episodes on the chat box. So please feel free to check the list of episodes. And of course, the registration, it suffices to register for episode 2 to the other episodes, since we have the same registration link. So once again, thank you and have a nice day.
Okay, thank you. Bye-bye.